Welcome to AI Paper Slop. For our deep dive today, we are jumping straight into a breakthrough paper. It's called MotionWAM, towards foundation world action models for real-time humanoid loco-manipulation by researchers from Mondo Robotics and HKS.
Right, and it's a big one.
It really is. So I'm going to give you the core insights right up front. MotionWAM basically solves two of the most frustrating bottlenecks in embodied AI right now. First, it completely eliminates this split brain architecture we've been stuck with and replaces it with a unified whole body latent space.
Yeah.
Which means the legs can finally perform actual task-driven interactions, like actively kicking a soccer ball instead of just, passively balancing the robot.
Exactly.
And the second thing, and this is crucial for real-world deployment, it makes these computation-heavy world action models run in real time. We are talking 4.9 hertz on a single A100 GPU.
Which is wild.
It is. And it achieves this massive speed up by just entirely bypassing the slow, iterative denoising process of standard video transformers. It conditions the policy on a single-pass intermediate denoising feature instead.
So if you are, say, an ML engineer or an AI researcher who's actively trying to get generative models to operate on a closed-loop physical robot, this paper provides a highly practical blueprint.
For sure.
Because, we've seen a lot of theoretically beautiful world models recently, right?
Yeah.
But bridging the gap between those massive foundational priors and the actual, harsh, low-latency reality of keeping a 40-kilogram bipedal robot upright, that is notoriously difficult.
Yeah, gravity is pretty unforgiving.
Exactly. But MotionWAM actually crosses that bridge.
Okay, let's unpack this baseline problem first. Because the robotics industry has been stuck in this hierarchical control paradigm for, years now?
Oh, absolutely.
So
Yeah.
why has it been so fundamentally hard to get a humanoid to do something that requires full-body coordination, like just stepping on a trash can pedal while reaching for the lid?
Well, the difficulty really stems from a huge mismatch in how we handle different physical domains. Historically, researchers have basically decoupled the policy into two completely distinct systems.
Right.
And they run at different frequencies. They have totally different goals.
Right.
So you have your high-level vision language action model, the VLA.
The brain.
Right, the brain. It processes the camera feed, understands the semantics of the room, and it sends highly specific, fine-grained joint targets to the upper body. The arms and the hands.
But it ignores the legs.
Totally. It doesn't control the legs at all. Instead, the VLA just sends these very coarse, high-level commands, like a target base velocity or a desired torso height to a completely separate low-level locomotion controller.
Usually built on, model predictive control or RL.
Exactly. MPC or reinforcement learning.
Which goes back to an analogy I love. It's like trying to play a high-stakes game of tennis, but your brain is only allowed to control your arms.
Yeah.
Meanwhile, your legs are being driven by a significantly less intelligent computer, basically a glorified Roomba whose only goal is to just make sure you don't tip over.
That is exactly what it's like.
And if you think about it, you are placing the upper body and the lower body into completely inconsistent action spaces. The arms get to interact with the complex 3D world, while the legs are relegated entirely to just balance preservation.
Right, because that lower-level controller is functionally blind to the semantic environment.
It literally doesn't see anything.
No, it doesn't know there's a soccer ball in front of the robot or a pedal or a cart. It's just receiving a 3D velocity vector and constantly calculating, how to fire the leg motors to maintain that vector without the center of mass falling outside the polygon of support.
So if you're the engineer writing this control stack, this explicitly rules out task-driven foot interactions.
Totally.
Because if the brain that actually sees the soccer ball isn't the brain controlling the individual knee and ankle joints, you literally cannot program the robot to intuitively use its foot as a tool.
You really can't. If the upper body tries to dynamically shift the weight to swing the leg and kick, that lower-level locomotion controller will actively fight that movement.
Because it thinks the robot is falling.
Exactly. Yeah. Swinging a leg rapidly looks like a terrifying balance perturbation to a system whose only job is to stay upright.
Wow. Okay, so that brings us to MotionWAM's solution, which is unifying the control space.
Right. Since dividing the robot limits its capabilities so severely, they just drop the upper-lower split entirely.
Yeah, just get rid of it.
Yeah, they introduce a unified motion, latent, so the system predicts whole-body motion tokens that encode everything simultaneously. I'm talking locomotion, torso movement, height regulation, foot placement, and delicate hand manipulation. All at once.
Okay, I have to push back on this, though, because any robotics engineer listening is immediately thinking about the curse of dimensionality.
Oh, for sure.
Like, if you map the entire humanoid body into a single continuous action space, and looking at the paper's supplementary data, they expanded the action dimension to 66 degrees of freedom.
Yeah, 66.
That is a massive search space for a model to learn. Usually, when you expand an action space that aggressively, the data just becomes hopelessly sparse.
It does.
The model gets confused by compounding errors, the robot twitches, and it falls over.
Yeah.
So how do they unify 66 degrees of freedom without the whole policy just collapsing?
Well, what's fascinating here is that they bypass that dimensionality curse by heavily constraining the model with a dynamic prior.
Okay.
They aren't just using, a vanilla feed-forward transformer that guesses joint angles from static images. That would fail. They implemented a dual-DiT architecture.
Dual-DiT, so two diffusion transformers.
Yes, a video diffusion transformer coupled with a motion diffusion transformer.
Yeah.
It's heavily inspired by the DITV config, actually. And by explicitly forcing the model to predict the visual flow of the video alongside the actions.
Oh, I see.
The actual physical reality of the scene acts as a massive regularization constraint.
So because it has to accurately predict the physical flow of the entire scene, meaning it has to know exactly how the pixels of its own arm and leg will move through space, it inherently learns coordinated whole body behavior. It can't hallucinate physically impossible leg movements because those would violate the video prediction parameters it's simultaneously trying to solve.
That constraint is the magic. It's what makes the unification actually work. And we see the proof in their real-world deployments on the Unitary G1 robot.
The videos of that are incredible, by the way.
They really are. Because the action space is unified under this dual-DiT, the G1 successfully executes complex, coordinated tasks that a decoupled system simply cannot process.
Like the pedal one.
Yeah, it dynamically steps on a pedal to open a lid. It actively shifts its weight to confidently kick a soccer ball. It squats deeply, using its entire lower body to load a heavy basket onto a low cart. In all of these, the legs are active, semantic participants in the manipulation.
Okay, but here's where it gets really interesting, and honestly, where the deployment challenges usually begin. Unifying the action space using a massive video diffusion transformer sounds incredibly powerful in simulation.
Right.
But world action models rely on video generation priors, which historically require iterative diffusion denoising.
Yes, the dreaded denoising loop.
Exactly. So if you are running a massive 2.5 billion parameter model, predicting noise, subtracting it, and looping that process like 50 times per frame, how on earth do you get that to run at 4.9 hertz on a single A100 GPU?
You really can't normally.
Right. If the thinking process takes that long, the physical robot will have already fallen over while it waits for the model to think.
Yeah, the latency of iterative denoising has basically been the grim reaper for world models in closed-loop robotics. I mean, a model that takes 2 seconds to generate an action is useless if gravity takes 1 second to pull your robot to the floor.
So how did they fix the latency?
The researchers solved this with a brilliant architectural hack. They call it the one-shot imagination regime.
Okay, let's break down exactly what that means. In a standard setup, a video world model is trying to fully denoise future video frames into perfect, pristine pixels, right? So the policy can look at that high-fidelity future and decide what to do.
Right, and generating those pristine pixels takes dozens of passes through the massive transformer. It's so slow. MotionWAM just flips the requirement.
How so?
The researchers realized the policy network doesn't actually need the fully rendered, high-fidelity pixels of the future to know what to do. It just needs the semantic and dynamic intent of the future.
The intent?
Yeah. So they installed a forward hook on a single transformer block to literally intercept its activations at a very specific fixed flow time step. Specifically, they intercept the hidden states at a flow time step where TOF is approximately 1.
Okay, for those of you working with flow matching models, TOF approximating 1 means we are at the very beginning of the generation process, right? Like the pure noise end of the schedule.
Exactly. TOF at 0 would be the fully resolved, noiseless data.
Right.
So by intercepting the activations when TOF is close to 1, they are taking the clean current observation, adding pure Gaussian noise to represent the future, and doing just a single forward pass through the video DIT.
Just one pass. Okay, to put an analogy on this, it's kind of like hiring an architect to design a building. Iterative denoising is forcing the architect to draft the blueprints, calculate the structural loads, and then painstakingly render the 3D textures of the brickwork and the lighting reflections in the windows before the construction crew is even allowed to pour the foundation.
That is a great way to put it.
Right. But the one-shot imagination hack intercepts the architect right after they've calculated the structural loads and drawn the raw blueprints. The construction crew, which in this case is the MotionWAM, looks at the math and says, we get the direction this is going. We don't need to wait for the window reflections.
That perfectly captures the mechanism. The video dual-DiT does one single forward pass, and the forward hook extracts the hidden states of the velocity network.
And those hidden states inherently encode the direction the scene is moving.
Yes, and the MotionWAM just ingests that raw intent and immediately maps it to the 66-dimensional action space.
And the performance delta is what makes this an actual breakthrough. In the paper, they compare this against Cosmos policy, right? Which is another world model-based policy with a roughly similar parameter count.
Yeah, Cosmos policy is a great baseline.
But Cosmos policy actually iteratively denoises the future video representations before producing its actions. And because of that heavy loop, it runs at 0.7 hertz.
Which is painful. I mean, at 0.7 hertz, a bipedal robot absolutely cannot maintain closed-loop balance. It's essentially taking a step, freezing for over a second, and then collapsing.
But by grabbing that single-pass intermediate feature, MotionWAM runs 7 times faster, hitting 4.9 hertz.
Exactly. It retains the dense physical understanding of a massive world model, but it actually operates at a frequency that allows for dynamic legged balance.
Okay, so architecture and latency optimizations are fantastic, but we have to talk about the data.
Always comes down to the data.
It does. We know that training a massive high-dimensional transformer requires an absolute ocean of data. And whole-body humanoid teleoperation data is incredibly expensive, difficult to collect, and rare.
Very rare.
You can't just scrape a billion hours of it off the internet like you can with text for an LLM. So why not just throw all the data into a giant pot and train it end-to-end from scratch? Like, if unified action spaces historically fail due to data scarcity, how did they train this without a catastrophic collapse?
We can't just throw a scarce, high-quality data set into a massive dual-DiT and expect it to learn physics from scratch. The model will overfit instantly. It'll just memorize the teleop data and fail in the real world.
So what's the fix?
The researchers design a highly specific 3-stage flow matching objective, and their ablation studies prove that every single stage is absolutely mandatory.
Okay, walk us through the mechanics of stage 1. They call it egocentric video pre-training.
Right, so in stage 1, they actually temporarily ignore the robot entirely. They take the video DIT trunk and train it on over 2,136 hours of cheap, action-free human and humanoid egocentric video.
Wait, action-free, so just video?
Just video. We are talking about basic first-person camera footage, people walking around reaching for things, navigating spaces. There are no action labels, no joint angles, just visual flow.
So they're basically forcing the model to build a gravity and momentum engine before it ever thinks about moving a motor.
Exactly, and it's a critical insight for the field. The initial bottleneck in embodied AI is not actually action diversity, it's egocentric visual dynamics.
Wow.
The model has to fundamentally understand how the world shifts visually when an embodiment moves through it. It has to learn occlusion, depth, spatial relations. And the ablation studies are telling here, if you skip this egocentric pre-training stage, the model's overall success rate on real-world physical tasks drops from 70% down to 59%.
That's a huge hit.
It just doesn't understand the physical geometry of the space well enough to operate in it without that prior.
That makes total sense. But stage 1 still leaves us with a model that is essentially a passive observer, right? It knows how the world looks when it moves, but it has absolutely no idea how to translate that visual understanding into a 66-dimensional motor command.
Which is where stage 2 comes in.
Cross-embodiment action post-training.
Yes, this is the bridge. They introduce the MotionWAM and train the entire dual architecture on a mixture of data sets from different robotic embodiments, not just the target humanoid.
Okay.
The objective here is to basically ground that massive visual prior into a generalized, unified action space. It teaches the model the fundamental translation layer between, I see the world flowing this way, and I need to move my limbs this way.
And what happens if you skip stage 2? Like, say you take that purely visual stage 1 model and try to fine-tune it directly on your precious high-quality target teleop data.
The policy completely implodes.
Really?
Oh, yeah. The ablation data shows that without stage 2, the overall success rate plummets to 42% because the model lacks action grounding. The jump from passive visual observation to complex whole-body closed-loop control is just too vast to learn from a small fine-tuning dataset alone. Stage 2 provides those generalized motor translation skills.
Which perfectly sets up stage 3, whole body teleoperation fine-tuning. This is where they finally bring in the high-quality, task-specific demonstration data for the actual Unitary G1 robot.
Right, because by the time the model reaches stage 3, it already understands physics, and it already understands how to translate vision into general movement. Stage 3 is just the final 10%. The specialization.
Honing the skill.
Exactly. It's teaching the model the specific kinematic quirks of the G1 hardware and the precise requirements of the target tasks.
Okay, let's look at the results of all this heavy lifting.
Cliff.
All that architecture, the TAF interception hack, the 3-stage training, it culminates in the real-world physical tests.
Yeah.
And the results against standard vision language action models are pretty staggering.
The gap is massive.
The researchers ran tests across 9 complex physical tasks, things like doing laundry, retrieving an item from a low drawer, and kicking a soccer ball. MotionWAM achieved a 76.1% average success rate, but the absolute best baseline they put it up against, GR00TN 1.7, only hit 43.9%.
Yeah, and the most revealing part of that data is where the gap is the widest.
Yeah.
The tasks that require the most holistic, whole-body coordination are where MotionWAM just dominates.
Right.
On the kick soccer test, MotionWAM outperformed the baseline by 40%. On whiteboard, which requires shifting weight through the legs to apply sustained pressure with the arm, it was 45% better.
But looking at the baselines, there is a fascinating, almost philosophical finding here regarding traditional vision language action models.
Oh, the VLM collapse.
Yes, they tested against Quen 3-DiT and Pi 0.5, which are phenomenal, state-of-the-art vision language models. Yet on the locomotion-heavy tasks, these VLMs virtually collapsed. We are talking success scores hovering under 20%.
Yeah, it was brutal.
Why do models with such incredible reasoning capabilities fail so spectacularly when you ask them to manage closed-loop whole-body control?
Because it really exposes the fundamental limitation of text-based semantic priors.
How so?
Well, models like Quen or Pi 0.5, they derive their intelligence from massive data sets of internet text and static imagery, right? They have incredibly strong semantic reasoning. If you show them a camera feed, they know exactly what a soccer ball is, they know what a trash can pedal is, and they could write you a brilliant Python script about how to use them.
But text is discrete and low frequency.
Exactly.
Loco-manipulation is continuous and high frequency.
That is exactly the problem. Knowing the dictionary definition of a pedal does not teach a neural network the microsecond by microsecond inertia required to balance a 40-kilogram metal chassis on one leg, while applying exactly 3 pounds of downward force with the other.
Right, the physics are just totally absent.
Semantic priors simply do not transfer to high-frequency, closed-loop physics.
Yeah.
By coupling the policy to a video world model's dynamic prior, MotionWAM bridges that gap. It relies on his learned understanding of visual flow and momentum, not internet text, to actually keep the robot upright and moving smoothly.
So what does this all mean for you? If you are building the next generation of embodied AI, MotionWAM provides hard evidence that world action models can actually escape the simulation lab and be deployed in real time.
Absolutely.
It proves that by intercepting the intermediate hidden states, you can completely bypass the paralyzing latency of iterative diffusion denoising. And most importantly, it proves that unified action spaces are the necessary future of legged manipulation. It unlocks behaviors that were just fundamentally impossible under the old master-servant hierarchical constraints.
Yeah. And I'll leave you with a final thought to mull over as we watch this space evolve. We've just seen that a robot can intuitively map egocentric visual dynamics directly to its entire body, treating its legs as active semantic tools rather than just passive stabilizers. So as we scale these foundational visual priors up, are we approaching a future where a humanoid's muscle memory for entirely novel, complex environments isn't hard-coded by engineers at all?
Oh, wow.
What if it's simply downloaded as a visual physics prior before the robot ever takes its first real-world step?
That is a wild thought. It fundamentally changes how we think about the relationship between seeing the world and moving through it. Keep building, keep experimenting with those architectures, and we will catch you on the next deep dive into the research right here on AI Paper Slop.